Right, I guess we can get started. So welcome to this talk. My name is Oyvind Tonsberg. I work at Cisco at Lysaker in Oslo. We make video conferencing equipment, and I'm going to talk about how we do some of our testing and how we do that at scale. So yeah, as mentioned, we make what we call high-end video conferencing equipment, basically for large meeting rooms at corporate customers, because it's too expensive to buy at home. Big screens, cameras, microphones, all the kit you really need to talk to people across the world. They are automatable. We talk to them over SSH or HTTP or WebSocket. There's a serial port if the network is dead, and so on and so forth. That makes it survivable, makes our job easier, and customers can handle them at scale again. So I'll start by talking a bit about how we're organized. Roughly in our main software repo, so we have an OS layer that's separate, but our main application that runs all the logic, business logic, and so on. There are about 200 developers that have been pushing code the last year. From last I checked, roughly 100 commits a day. So it's reasonably busy. And we also roll out code to actual meeting rooms every single day. So there's a bit of testing to be required. I checked our main repo. It's roughly 250,000 lines of code, so it's not huge, but it's not small. And the last month, we had 190,000 changes, about as many additions and deletions. So it's quite a busy code base, in my impression. So the illustrations on the side are from our labs. So these are some microphones and some of our touch panels that are just racked up for accessibility. So I'll get back to how we talk to this. Just for show. Yeah, so some testing required. We're organized in teams, as most people are, I guess. We do what we call fully featured teams or something. I don't know, it's flavor of the month. But basically you have application developers, you have testers, you have UI specialists, UX teams, and so on. So sort of everything you need in a single team to create a new feature and push that out to customers. And each of these teams own their own tests. So a subset of our system tests are testing their features. So if you're in the first-time setup thingy, you own all the first-time setup tests. So the same team that develops the feature will also make sure that the tests are safe or sane and kept up to date. And that's how we keep people honest, and you avoid everybody having to know everything all the time. We also have a dedicated tools team. They work on our CI, continuous integration, continuous development pipelines, all our tools. Well, we actually have two teams because we have an internal IT team that runs all our servers and network and all those things too. But yeah, we need everything to make things run. The core tools team is like 5 or 10 people. It has been that for many years. So you add some new services and you maintain the ones we have and so on. And yeah, just please interrupt me at any time and ask questions. I want this to be interactive and ask fun questions. So thank you. Yeah. So a couple of developers, a more QA specialist, some that work more with UI, depending on where you are in the team and so on. So we do, yeah. So a team is like 5, 6 people, like the average pizza sized, has been mentioned before. Yeah, fair enough. Well, historically it's been more of a clear split, and some teams, everybody does everything. In other teams, there are more dedicated test focus and more dedicated development focus, and there's flexibility to do both, as long as we end up in a good place. And as part of taking turns in different roles is we have this thing we call triage duty. So a representative from each feature team, basically, will take turns to be on sort of first-line support for failing tests that week. So most weeks it's not too much to do, but there's at least one point of contact whenever something weird is going on. You have someone to ask, and that helps when you're a somewhat large organization. And it's also a good way to spread knowledge inside the team, because then you need to see tests you didn't write yourself or that you inherited from someone 3 years ago that nobody really knows how it works anymore. But suddenly you have to find out because it's failing. And that's a good way to keep the knowledge alive in the organization. Even though it's slightly interrupt-driven. Yeah, our current policy, it's fine to break things. But when we notice you break something, please just revert it right away. Because we try to keep the main branch of our software releasable at all times. And if you're broken something, you try to fix it right away. You're panicking, you're trying to figure out if it's okay, you try to build something and push it. And don't stress with that. Just roll back whatever you did, take your time, figure out the real problem, and solve it in a nice way, and then push it again. It keeps the resting heart rate down for everyone. Challenge is, how do you know when you broke something? And that's sort of the million-dollar question at all times. Keep the feedback loop short. You want to know something is wrong, either the moment you're typing it, but that's hard for the real problems. So we do testing at layers and layers and layers and layers. So there's a lot of automation and a lot of eyes observing, looking, following. And a mixture is always needed to catch the things that you haven't automated yet. That's the core point here, I think. Should I talk to my? Yeah, so again, we try to keep the main branch healthy. We try to avoid, oh yeah, we could just have it fixed and then you do a branch and suddenly your Git tree is horrible because you're just quick fixing this and then you have hotfix branch 1, hotfix branch 2, and yeah. So we try to keep the shared code base healthy and branches to a minimum, only like long-term release branches and so on. To go through a bit more details how this works in real life, we'll follow the life of a commit. So picture a new developer. They're pushing their first feature ever. Maybe it's a tiny bug fix. Maybe it's a giant new button or something. I don't know. But we make rather complex systems. They have a million variables and configurations and various use cases that should work. So if you tested the stuff, your feature works, you know that you push a button and the light goes on or the new app opens or something, but how do you know that you didn't break anything else? And again, that's the good question. So the flow of that is you'll build locally or on a build server. We have a few of those. They have silly amounts of CPUs and memory. There's an example there. And we build a lot of different artifacts. I think when you do a build all system, you'll create almost 70 different artifacts, depending on, and that includes unit test targets, module tests. Roughly 10 of those artifacts will be running on real hardware afterwards, and the rest are for unit test and various system level analysis and mappings and metrics, and I really don't know because that's not my core area, but you can ask others and they will help afterwards. So in this talk, I'll mostly be skipping over all the low-level testing we do. I mean, there's a lot of unit tests. There's a lot of like module, low-level compile time testing. I don't know how that works. We use a lot of it, but that's not the focus of this talk. I'll be focusing on what you do once this code runs on real hardware and how we can run it on a lot of hardware every single day. So you push code, it'll build, as aforementioned, 50, 70 different targets. The full build takes an hour or so from clean, but we use incremental builds, so it's faster because you only build the difference from whenever last time that server was busy. Yeah, we have like, that's a total build pipeline, or that's the available server pool we have for compiling our software. So like 5,500 cores, 32 terabytes of RAM or something. It's a rather silly number. It was fun to find. So we like throwing hardware at problems, in case you hadn't noticed. Yeah, because we have like 40 nodes or something in that cluster now. And that's there. So our testing runs on a multi-stage pipeline. So we have labs with loads of devices. And those pipelines have a lot of stages. So we have circuit breakers, that we like to call them. So, you know, if the first, you build something, it compiled, it linked, it's probably fine, right? So we'll upload it to a single device and boot it. Does it go boom? Then we stop testing at that commit. Because we'd rather not have all of these go boom at the same time, because it's a royal pain to recover. So we design circuit breakers. And then we test on all the different variants of products we have. So large, small, and different hardware platforms and so on, to see if it's healthy. That goes fine, we'll continue on. And every single of those hardware-based tests will reserve one or more of these devices. It'll reset it to a known configuration. It'll upload the new software under test. It will boot it, see is it still working fine. And then it will run the actual tests, which would be like dial somewhere, see that you get media, or yeah, we'll go through some examples here. Just, can you still register to WebEx or Microsoft Teams or whichever calling service you want to use? Can you dial in conference? Do you get media? Do you send media? Can you plug it into a Mac Mini and have it as a USB camera as before? If I'm running a super high load scenario, am I still able to encode 60 frames per second as it should be? Or do we have some research challenge with your new change that is causing a problem due to the total load being too high or something? Is the screen actually rendering the UI, or do we just think it is? So we have some systems where we put a selfie stick with a camera in front of the, or a mirror in front of the camera, so it can look at its own screen, and we'll show a QR code, take a picture of it, and then you're really verifying glass to glass that everything is actually working in hardware, rather than the software saying, sure, I'm sending all the bits over here, and they're not showing up because somebody forgot to turn on the backlight. So again, redundancy, coverage at depth. That's really what we're after here. Yep, so we'll carry on. So a single commit will start about 700 of those type of tests. And some data again on that. An average test takes 6 to 8 minutes, including the software upload and running the small script. And I realized that's more than 3 full days of device hardware time for a single commit. We do, of course, run a lot of this in parallel. And a test might book 1 or 7 devices, depending on the scale of the problem. So, yeah, that's a fair bit. We do also have a fair bit of virtual systems, of course. So if you can run your test on a pure software variant of our application, just checking that signaling works or something, that's a good thing too. But at some point, you also want to verify that it actually runs on the real hardware without problem. So we do a mixture. But then we try to move more things further down the pipeline, so you don't have to do absolutely everything on a single commit. Question?
Is this after the commit goes to main, or is it still in a PR?
We can do both, actually. So it's a default behavior whenever you push into main, but we also support running this very pipeline or a subset of that pipeline on your change in the PR before you push the main. So you know, so if you're wondering, will I break a bunch of things when I push this? We have the opportunity to, with the same tool system, to run a test on your pull request to verify. I know I've been fiddling in this part of the media code, as well run some media-related tests and see if they break something, or you can run the entire gate.
So that's something that is left to the choice of the developer.
Yes, we leave that choice to the developer. I should remember to repeat the questions so recording works. So yeah, that's a quite popular feature we have now. So using GitHub for pull request, and that will also build everything the same way, using the same build servers and offer that up. Yes?
Is there a way of tailoring the run that the developer orders just to cover certain domains?
Yep. So our tool allows you, so one of these 700 tests, we call that a gate of tests, or that's our gating set of tests, and it contains a dozen or 20 plus whatever suites of tests. And each of these suites is typically owned by one of the feature teams. So you can pick and choose the ones you want, or you can run single tests. So flexibility is there. And if you're feeling confident, just push the main and it's probably fine. And if not, someone will yell at you. Yes?
Every commit triggers all the tests, or do you have to choose?
Every commit triggers all of these tests, because this is a small subset. Again, yeah. This has been growing rather fast over the last couple of years, so we need to continuously go through the total set of tests that we run on every commit and consider, should we merge some of these tests together to a single one? Should we move some of them further down the pipeline, and so on? But the main motivation for running them all this on every single test is that you get the faster feedback loop. That's why we've thrown more hardware at the problem. And you make it way easier to bisect something because you notice that the test breaks a few hours after the commit came in. And then you can easily go back and see which test broke it and either revert it or update the test if it was a desired change, or so on and so forth. So we keep our test repository and our main code repository separate. So the downside of that is that you need to make sure that your test can handle both the previous and the next version of a feature or something. Upside is that you can fix the test straight away, especially if it breaks due to a change that wasn't in our main software repo, but somewhere upstream. Because there are a lot of external dependencies when you do this. So either some registration logic changed in our WebEx cloud or some of the other clouds we're talking to or something. And then you have to fix the test or one of the two sides. But having the flexibility to do this asynchronously makes it easier to get working code out faster and more often. As I said, we can run 800 of those tests in parallel. So we have a lot of virtual workers that will download the test script and run the code from there. But we don't have infinite hardware, so we need to do some clever scheduling to make sure we get a reasonable throughput rate. So we try to prioritize the most recent commit. So, and then we do like every 5th commit backwards has higher priority. So you'll get some bisect data, and then we'll backfill out the remaining stuff as we go along. And we try to keep up throughout the day so we don't get too horrible backlogs. But the challenge there is to make sure that the tests don't all want to run on the same single device that has this special cool thing that everybody likes to play with. And we either have to get more special cool things so we can do in parallel, or we need to rebalance and restructure. So that's a never-ending story to keep because we can't really dig out more labs underneath our office anymore. It's kind of stuffed. I really want like a 3rd layer of the garage just for more test equipment, but I just don't find the budget for that. So yeah, we're stuck with what we have. All of these tests, we have a goal that they should be reasonably fast since they run on every commit. So we'd like the feedback loop to be 10, 15 minutes. So if you're the first test that day, you should get everything done after, most tests will report in like 20 minutes after they get the artifacts they need. And the last ones should be within a couple of hours. So you should know if you've broken something within a couple of hours, like anything. And you'll have a good feeling after half an hour. And this is after you've run your unit test locally and verified that your part of the logic is sane, of course. But again, not talking about that. We also have the next stage of our pipeline is something we run nightly or after work hours, because when you fire off 2,500 of those tests, it sort of strains our network. And if there's a really cool customer demo in the same building at the same time, they get grumpy because their video doesn't work. So we mostly run that at night. In this test, we typically run the same tests, but on more products. So in the early stage, you verify that it works on at least one of our systems, and then you test it works on all the others at night before we release. You'll have longer tests doing longer calls where the feedback loop would be annoying to run on every commit, or we just don't have enough of that special hardware type to run on every commit. Then it's sort of delegated to the next stage. But this is still before we release to customers or internal users even. So yeah, so the goal is to have a daily release to developers, meeting rooms in the office, and so on and so forth, because that's sort of our next stage in the pipeline. People using our latest software looking for issues, and it's something that looks off, something we didn't have test coverage for. And yeah, I can also mention that in this stage we do more UI flows. We have expensive tests. We use something called Applitools, which will take screenshots of the UI in various stages of the flow and do pixel comparison to a known baseline. So you'll see if somebody did an off by one calculation error and some buttons are moving a bit and so on. And this is sort of AI-based. You can say that the text strings are not relevant to look at, but you want to look at bits and so. So they're high maintenance, they're a bit annoying to work with because they fail a lot, but they're also really nice to catch visual issues before or automatically. So, tools are fun.
Could you repeat the name of the tool?
It's called Applitools.
Appli.
Yeah, like application Applitools. And yeah, and in a perfect world, if all these tests happen to pass, the only thing a human would need to do is to say, yeah, this looks good, let's push it. In reality, there's usually not more than 1 or 2% of the tests that actually need follow-up. Like the first run might have a higher failure rate, but then we can rerun the red ones once, and if they're not always failing, it's like somebody should look at it, but it's not blocking. But 1 to 2% out of 2,500 is still quite a few. So there is a manual component to this still where we need to talk to the different teams. Can you figure out why this one is failing? Can you look at that one? And then get back within a few hours. So that's kind of the remaining chaos management that we haven't fully automated out yet. But a lot of stuff is actually passing these days. It's a bit worrisome. But still cool. And why do we bother? My main argument is that when you're working with embedded systems and you've sold a few 100,000, it's real hard to just send them a bit more RAM because you need a bit more. So we need to make sure that we don't exceed our hardware specifications. And our systems are supported for almost 10 years. The oldest still supporting ones, we started shipping 8 or 9 years ago, I think. So there's a fair bit of lifetime where we need to work with reasonably old hardware that should still support most of our new features, and then we need to do some balances whether, no, you don't get the new cool thing, but these do, and so on. But that's also marketing and not my problem. But again, the main goal is to spot the changes you didn't think about. So a classic quote from, yeah, most people I work with. I had nothing to do with that failure. It can't have been me. But then sometimes it ends up showing that, well, it really bisects to your, oh yeah, that's strange, okay. So that's how it is. So let's talk a bit about tools. How do you do this? Again, more labs. Labs are fun. Most of the stuff we use have been developed in-house because we've been at this for a while. I've worked for almost 15 years now, and stuff was old when I came in. But back then, I mean, we had a 9-month release cycle, and every commit we ran one test to make sure that you could still do a basic call. So things have escalated slowly and steadily from that. Main benefit of making everything yourself, you get exactly what you need. You get to design it, create it, and maintain it all by yourself, which also happens to be one of the downsides. But we have a lot of fun tools. The next talk in this room will be on our automated failure analysis and crash analysis tool. That's very cool. I recommend sticking around. So I'll not talk too much about that because that would be spoiling things. But we have a bunch of other things I'll skim across afterwards. We do use some open source tools as well. I mean, we have some Jenkins in the pipeline, but Jenkins wasn't even born yet when we started doing this. Jenkins is from 2011. So had we started over from scratch today, we would probably pick more existing tools and so on and so forth. But yeah, we are where we are today. This is how we do it. We use some Kibana for like meta analysis across tests and just massaging data and so on, but not too much. We use Selenium for driving our UI-based testing on the web interface. Yes, like I mentioned, our devices have like touch panels for most users. We have a web interface that admins can use or users can use to dial in. If you don't like using a touch, we have and more low-level APIs. I'll get back to those actually, but not right now. Yeah, so to go through basically the building blocks of the tools we have services for booking those resources, like devices. I would like 3 of that one. Make sure it has a camera. No microphones, please. That same service is responsible for making sure that it's healthy at the start of your test. And if your test goes boom, it'll clean up after you and get it back into a sane state so the next test can use it in a few minutes. Defining tests, scheduling, executing tests, collecting the result afterwards, presenting them in various views. Mostly just websites with databases, which is really derivative, but yeah, it's sort of what they do. Clever and fancy and quite useful, but again, they're custom to what we do, so I'm not going to go deep into how they look and how they work, but the ideas are there, and we can talk details if you're curious. So again, always open for questions. And a bunch of test automation libraries. So we have, so scheduling is either commit-based or you could do time-based scheduling. So either I want to run on every commit and block a release, or I would like to run on every 10th commit just to collect some data from our team, or I'd like to run every Tuesday at 3 p.m. because I like regularity and cron is nice. So again, flexibility depending on the use case of the test. Our test automation libraries, everything is Python-based. Some of the websites are Ruby-based because Ruby was cool some years ago. But it's mostly Python. So again, developed in-house. The core test automation tool was developed sort of like an open source project across different sites, some in Oslo, in the UK, and some in the US. So it's sort of been driven like an open source project. Nobody had it as a full-time job, but it's been quite interesting. But it's also been a fun challenge to see how you need to keep recruiting new people to keep the tool well alive. And when your pool of possible recruitees is within the company, it's a fun challenge to find like people that say, "Ooh, this looks fun," especially when the code base is more than 10 years old and a bit scary. But that's how it is. So the test automation is really about driving it through existing APIs. And it's not defining a test API, it's using the core API that we have in our products. And that's one of my core, one of the things I really love about the systems we make is that they have a single API that does everything. So there's an application and there's a thick API layer. And then on top of that, you can put the UI, you can put the web interface, you can put the terminal interface, you can put the control systems from the cloud, and everything drives the device through the same APIs. So you can write all your tests just interacting with that low-level API. And majority of the API is also public, so customers can play with it and create their own things on top. And everything going through the same layer means that it's well tested, it's well defined, we're pretty sure it works most of the time. And designing good API is hard, so a lot of people spend time thinking about adding new things, and it's been designed into the code since forever. So as with security, designing in things early is way easier than slapping it on at the end. It's been interesting to test with like other parts of Cisco equipment, like phones that are not, well, they have cost is a priority above everything else. So APIs are like, yeah. So we added support for that too, but their CPUs are weaker, the code base is smaller, so it's a challenge to work. But our tools support talking to them as well, so you can set up tools with or calls between quite different things and still have them talk together. So that's quite fun. I think that was it. Yeah, and another benefit of that API is that you force the logic away from the UI layer as much as possible. It's great to have UI logic, but it's easier if the UI is just reflecting the state of the total application. And then you can do, UI-based testing. And when you're developing a new UI, part of that, you should, and we have tools for that. So we can like dump the state of the UI, find the names of the buttons, and click on the buttons, and go through those flows. But if that's the only API you have, it's a royal pain in the ass to always have to use all that. So we do both, because testing at layers, like the NASA talk yesterday, every layer removes about the same percentage of bugs from the code. So more is better, as long as you have time and space and hardware. But it's, again, as your previous talk as well mentioned, that the UI will always be changing because it's fun to draw new buttons. And whenever that changes, then if you need to change all your tests, then ouch. If only the team that is designing a new button has to update their own tests, then they feel the pain and they balance it out, and the others don't need to worry. So, and another nice thing about our API is that you can subscribe to events. So there's like a feedback system. So you can set up your test to click a button and then wait for an event to come back and then carry on with your script. And that's one of my favorite features, especially when you do it asynchronously with 10 devices and they all tell you when they're entering a call. So no polling, no magic sleeps, unless you want a call to stay for 30 minutes and then carry on, then you can have a magic sleep. But again, it feels like healthier software and scripting when you do that. And then putting culture all the way at the end here, but it's really one of the core things. Like, I mean, you need the I'm talking mostly about tools today, but people, as has been mentioned many times this conference, is core as well. Long-lived software, a long-lived culture of people that care about that software. That's really, yeah, I feel that makes a lot of the difference. And then we've been growing this for many years, so we fix one problem at a time. We try not to over-engineer too many things. It's more like, oh yeah, can we make that a bit better? Can we make that a bit better? And then suddenly we have this. And it's a quite nice support framework for all our developers, so they're not too scared of doing things, even with rather complex software that we make. Yeah, and again, testing is first-class citizen. They're in the teams. It's in-house. People care about their tests. They care about the features. The risk is, of course, that the testers are too fond of new features, so they just verify that the green path works happily. So you have the challenge when the testers are too closely integrated with the feature team, is that they know how it should work, rather than, how can I break that? So you need to make sure you put on the right hat at the right time in those roles, and be the evil code monkey, chaos monkey that will just try to break things. But again, some things you can do on the hardware system level, other things you'll just cover in unit tests. do evil things in unit tests, it's cheaper. And the feedback loop is faster, but yeah. We also do like reviews, and can people from a different team come in and just look at what this new feature has of test coverage? Does it look sane? Do you have so we try to like cross-check each other a bit. Then we can talk about some scaling challenges. Because again, we're not growing more labs, so we just stack things real tight. These are 55-inch touch panels. Stacked like this, you can slide them out. It's sort of like a blade server, homemade, on pallet systems. And again, that's how you get a fair bit of hardware into a reasonably limited floor space.
Does condensation also fall under cooling, or is it a separate? Is condensation a cooling issue, or is that a separate issue?
Oh, we don't really struggle much with humidity. It's quite right. It's the whole building is real dry.
You're lucky.
Yeah, it's actually a bit tiresome. Your eyes dry out. But no, we haven't had well, we had some at some point, but I think it's been sorted out. But yeah, let's talk about power. So back in the days, we would use those. Your usual power strips. You can fit in like a dozen of normal Truco plugs. The scale's 5 you can load it up to 16 amp standard fuse. Fun thing is that when the first power outage comes along and you have 40 of those 12-volt power bricks, and when you turn on the fuse again, that looks a whole lot like a short circuit before they are loaded with enough power. So then you're flipping the Class B fuse over and over and over again until you have power out. And that's very annoying. So you scale up. Industrial PDUs. So these have a real nice feature. So when you power them on, they will do there's like an internal relays. So they go turn on one at a time, and you avoid the giant spike at the start. They also have a real nice feature that the fancier ones have a network interface and a web API. So you can remotely log into them and flip off whatever is on port 16. So if you remember what you plugged there, you can do a hard reboot remotely. We really leaned on this during COVID when we couldn't go to the office. That really pushed us into the last bit of, can we automate everything? They're not super cheap, but neither are having 20 engineers running around and pulling cables. So, but when we literally have 1,000 devices in our lab, you can't remember what was on which port. So made web interface for this. Reasonably easy. I think we have 2,700 devices now, 200 of those PDUs in the lab. So there's a web interface. You can just search up either by a host name or MAC address or whatever to the device you're looking for, figure out where it is, flip it on and off again, check if it's actually on. So the first time you add them, somebody needs to fill out the database saying this device is plugged in this cable, because there's very little data communication on 220 volts. You can't send a host name across. So there's some manual labor required, but usually a one-time thing. And yeah, let's talk serial ports, because that's also fun. So when I started, every single new device we made had a different serial port. You would have DB9 plugs, you would have sort of Ethernet, but not really, because you needed this custom circuit board and then a DB9 plug. You would have this one's real fun. This is a HDMI cable with a kind of thing on the side that could either be camera control or a serial port, depending on a magical. I think you needed a remote control combination. You turn on the red light, evil dark mode or something. So we finally standardized on micro USB for every single new device, every single new product, because then you can use the same cable. And then you can plug a lot of them into a very big USB hub. The standard supports 128, 27 devices, but that doesn't mean 127 cables, because each device will have 3 virtual devices or something. So that's another fun challenge. And then you also need to figure out which /dev_TTY USB maps to which device. So made some scripts to log in, figure out what the serial port of the device, or yeah, to do some automatic mapping and discovery and so on. And again, this too, following a pattern here, when you have some thousand of these, you set up a bunch of devices, small lab PCs with hubs, and a web front end to figure out which one is where, and so on. And we'll also, so you can basically SSH into this alias, which would put you into a screen session that was connected to the serial port. So you could SSH onto the serial port on the device, even though it was offline. So it's a quite nice hack. I like it. It saved me a lot of trips up and down the stairs. I think that's basically what I had. So I'll say thanks and open for more questions. Yes.
Do you also